very much, Katya, for the very nice introduction. And thank you, Katya, for inviting me back to ECI seminar and to give this talk. I'm going to talk about stable determination of the time-dependent clearing kernel in nonlinear Boltzmann equation. So my talk is divided into 4 parts. In the first part, I'm going to talk about what are inverse problems. So what are inverse problems? Given a medium, maybe a human body or a non-transparent industry object or the Earth, whose internal properties are unknown, one needs to extract internal properties from external observations, and we can use the various external observations on its boundary or far away to extract internal data, and including this electrical observation, acoustic observation, and optical observation. So the kind of problem where electrical observation is used to extract internal data is known as electrical impedance tomography, which is also known as the Kandaran problem. In 1980, Kandaran asked the following question: is it possible to determine the electrical conductivity of a body just by making voltage and current measurements only on its boundary? And this electrical impedance tomography has a lot of application in medical imaging because people's human tissues have different conductivity, electrical conductivity, and when there is unhealthy tissues, the conductivity of the human tissue will possibly be changed. And this can be used to monitor brain activity, heart activity, and lung perfusion. And it can also be used to detect cancer. And besides this electrical observation, we can also use acoustic waves by collecting echoes to get internal information. So one example is that I put a seismic vessel in the ocean, and using an air gun, we can generate some acoustic waves which can be reflected by the Earth and then collected by those hydrophones. So the question here is, given the seismic data collected in the ocean, what are the maps of the Earth's interior? And we can use this to infer the location of oil and gas. And another application for this acoustic waves is it can be used to extract the shape of the vocal tract by measuring the salt pressure at the lip. And other than this, we can also use optical observations to get internal information of a body. So in optical tomography, near-infrared light is sent into biological tissues to probe tissue structures, and outgoing photos are measured. So what we want to know is what is the optical property of the tissue. And this can be used to diagnose abnormal tissues in some soft tissues, for example, in the brain and in women's breasts, and also in finger joints. And those different models using different external observations can be modeled by different equations. For example, this electrical impedance tomography, it can be modeled by conductivity equation, and this acoustic waves, it can be modeled by wave equation, and this optical tomography method can be modeled by linear Boltzmann equation, also known as the radiative transport equation. So for the purpose of my talk, I will only focus on the inverse problem for this transport equation. So this is the part about inverse problems. So next, what I'm going to do is I will continue to talk about inverse problems for linear Boltzmann equations. So before I introduce the equation for linear Boltzmann equation, I want to first introduce the free transport equation. So what is a free transport equation? So we let this f, which is a function dependent on time, position, and velocity, to denote the density function for some particles. And if you have a bunch of particles that are traveling at velocity v at position x and at time t, then after time s, there will be the same bunch of particles will be at this position x plus dv and at time t plus s with the same velocity v. So what is this thing here is this function cs dependent on s. This is always a constant function. If you differentiate this function in s, you get the free transport equation. So what is a linear Boltzmann equation? So this free transport equation, it describes the travel of some particles in a vacuum. But if it's not vacuum, the particles or the photons, it might be absorbed by the surrounding media. And it may also change the velocity due to some scattering. So instead of the free transport equation, we are going to add a lost term, sigma, which is called our absorption coefficient, to describe the loss of a particle with velocity v due to the change of velocity or absorption. And because the velocity can be scattered into other directions, so what we are going to do here is we are going to add another term, which is our gain term, which describes the probability that during a scattering event, a particle from another direction, v prime, scattered into my direction v. So this is my linear Boltzmann equation, and our setup is an open-bounded convex domain with smooth boundary in Rn, and this is our domain of the position x, and we are going to denote another set v to denote the space of our velocity. And now we denote this u as the space of the position x and the velocity v. And we also would like to define the incoming and outgoing set of my boundary. So what we are going to do here is we pick a point on the boundary of my domain, and we look at the velocity that is paired with this point. If at this point, the velocity is pointing into this domain, then we see that this pair is in my incoming set. And if this velocity is pointing outside my domain, we see this pair is in its outgoing set. Because we are talking about dynamic problems, so I'm going to let t denote capital T denote my time, and I'm going to denote all the corresponding space respect to this time interval from 0 to capital T. And then we can formulate our initial boundary value problem for the linear Boltzmann equation. So we put initial data equals 0, and we put some incoming data G on our incoming set, and our F, which is the density function of the particle, satisfy this linear Boltzmann equation. And this problem is well posed under certain conditions. For example, I'm giving you one condition that this forward problem is well posed. If you can check those three conditions, and then we can see that there exists a solution F such that this F is continuous in T with values in LP space. This T can be from 1 to infinity, include 1 and infinity. And then we can define our measurement operator, which we call this our about operator A. It maps this incoming data G to our solution to this initial boundary value problem restricted to on our outgoing set. So note that this is only on the incoming and this is only on this outgoing. And the question here is, can we determine this absorption and scattering coefficient sigma and k from this about operator A? And more precisely, the question we would like to ask is the following. So first, uniqueness. If we have two about operator, they are the same, does this imply that the corresponding absorption and scattering coefficients are also the same? And we also would like to know the stability result. If the about operator are close, do we know that those two pairs of the scattering and absorption coefficient are also close? And can we have a reconstruction procedure of this pair sigma and k from about the operator A? And do we have some partial data results? If A is only defined on a subset of this incoming set and measured on a subset of this outgoing set, how would this influence the previous result? And now let's look at some previous literatures. So first, I will introduce the previous literature on linear Boltzmann equation, but only for stationary case. So which means everything is independent of time. And in both the stationary and non-stationary case, the uniqueness result falls in general for this absorption coefficient sigma. And the best we can hope to determine is the sigma is a function dependent on x and then the f value of v. And the first uniqueness result is given by Charlie and Stefanov in 1996. In particular, they proved that when dimension is greater or equal than 3, we can get a uniqueness result for the absorption and scattering coefficient. But for dimension n equals 2, we only get uniqueness result for absorption coefficient. And this the uniqueness for scattering coefficient k was later completed by Stefanov and Gunther in 2007. And the reason why this k, and also under the condition that this k is small, why this k is so difficult from the sigma when you have dimension 2. The reason is in dimension greater or equal than 3, both sigma and k, those two functions are overdetermined by the information we are having. But in dimension 2, only this absorption coefficient is overdetermined and this scattering coefficient is formally determined. And we can also have some stability result, and different from the stability result for elliptic equations. For most of the stability results we get is of logarithmic type. But for transport, for linear Boltzmann, this kind of transport equation, the stability result we get is of Holder type. And the first stability result was given by Jin Wang in 1999, and it was proved for the scattering coefficient k is independent of velocity. And later this was generalized by Ball and Jolivet in 2008 for general k, when this k also depends on this variable x. And for dimension n equals 2, this was done in the same paper in the Stefanov Woman 2003, same paper. They also gave us stability result. And what I also want to mention here, for the uniqueness results, this dimension greater or equal than 3 and dimension equals 2, their proof is constructive, which means a reconstruction which means the reconstruction problem is also solved in those two papers. And next, I would like to move on to talk about previous literatures on linear Boltzmann equations, but for dynamic case. So let me only mention that the first uniqueness result was given by Charlie and Stefanov in the same year, 1996, and their result is constructive, and the stability result is given by Ball and Jolivet again, but in 2010. And besides this original linear Boltzmann equation model, and more general models have also been considered. So models with time-dependent coefficient was studied by Bellisold and Bengoja in 2009. So they first studied when this absorption coefficient depend on time, and then in another paper they studied when this scattering coefficient depend on time. And in the first paper, they gave a uniqueness result and a logarithmic stability result for this sigma. But if you want to recover information about the scattering coefficient, you need to further assume that the scattering coefficient has a product structure. So you split this part depend on x, and this is an unknown term, and you assume that this kappa part, which depends on this v prime, v are known term to us, and only this g part, which depends on x, is recovered. And in this case, when they study the scattering coefficient depends on time, they can only study the case that where the scattering coefficient as a product structure, and you split this time and position part as your unknown, but assume that this kappa part, this v prime part, is something that is known to you. And another kind of model that is studied under the same situation, based on the same linear Boltzmann model, is the model with nonlinear terms. So instead of your linear Boltzmann model, you add a term which depends polynomially in terms of your f. And this was studied by Ruyu Lai, Gunther Ullmann, Haiming Zhou in 2022, and they gave both uniqueness and Holder stability result. And in their paper, both the linear and nonlinear terms can be uniquely determined, and they use the methods of a linearization method and also use kernel estimate. And now what I'm going to do is I will give you a brief idea how to prove this inverse problem for linear Boltzmann equation, but only in this stationary case. So this is based on a proof of Charlie and Stefanov in 1996. If you think about this stationary linear Boltzmann equation, the solution to this stationary linear Boltzmann equation, when you put some incoming data as a delta distribution, can be splitted into three pieces. So the first piece is a function that satisfies this free transport equation, but with some boundary data as your original boundary data, which is a delta distribution in x naught and v naught. So you emit some point source, some light beams at this point x with velocity v. And this is f2. And f2 here, it satisfies this free transport equation, but you have this non-homogeneous part. You have this scattering coefficient, but with boundary data 0. So what we are going to do here is we look at this line. We look at particles moving in this direction. This will give us information for our absorption coefficient. And then if we look at particles moving here and then scattered into another direction, this will give us information about the scattering coefficient. So more precisely, what I'm talking about is when dimension n equals 2, the most singular part in the Schwarz kernel of this about operator determines F1 on this outgoing set. And in particular, this F1 restricted on this outgoing set can be represented by an exponential function. Here you have the X-ray transform of sigma, but you have another factor for your V dependence, and then you have a delta distribution. So now if you pick a point xv on the boundary, so this can only be 1 if you just go from x and you go, so this is, you find a point here and you just go along this direction, time go back to your initial point. Here you just integrate. So this tau minus is, okay, so tau minus is the exit time. If you go from this, if you have a position x and the velocity v, and then this tau minus is the exit time, you go from this minus v direction, and this tau plus v is you are at xv, but you exit along this v direction, and this is measures the exit time in this direction. So if I pick a point on the boundary, what it's saying here is the observation for my term is my outgoing velocity must be the same as my initial velocity, and this point here must be the point that I go straight line from my x naught. And when dimension n equals 2, so from here, if we get information, this is known and this is known, then we get information for this X-ray transform for my absorption coefficient, but just we have one extra parameter. And to uniquely recover this scattering coefficient k, what we are going to do is we are going to look at the second singular part in the Schwarz kernel of the about operator, and this determines F2 restricted on the outgoing set. And here, if you look at this delta distribution part, what happens is we are at this point xv, and then we first go by s time, and then go back to a point that is on this straight line, and then we go from there to check the exit time at this point in this direction. So this comes back to this x naught, v naught, my initial point. So because now this sigma is already known, and then this part is all known, and then we can get, this is the X-ray transform of my scattering coefficient. From there, we can recover this scattering coefficient. So next, what I'm going to do is I will move on to talk about inverse problem for nonlinear Boltzmann equations. So instead of this loss term and gain term in this linear Boltzmann equation, for the nonlinear Boltzmann equation, we are going to consider this Clarion operator QF. So this kind of nonlinear Boltzmann equation, it describes the evolution of a dilute gas with binary collision between particles. And here, this Q term is a quadratic term. It contains my Clarion kernel K, which is a function depending on all the variables, my time, space, velocity, and the U is the velocity of another particle that I'm going to have Clarion with. And this U prime and V prime is the velocity after the collision of two particles. So this term, this positive term, this term describes that you have this this minus term, it describes that we have two particles with velocity u, with velocity v. They are going to have a collision with each other. So after the collision, you will lose the velocity in this direction v. So that's why you have this minus term. But the collision we are considering here is all elliptic, which means you can inverse them in time. And so in the same way, if you originally had u prime, v prime as two particles, they can collision and give you the velocity u and v. So you have some gain in the direction of v. So more precisely, the collision here is elastic and it preserves momentum and kinetic energy. So this part is momentum, this part is energy, and this system is underdetermined, and a convenient way to represent this is we introduce another parameter omega of dimension n-1, and we denote our post-collision velocity u prime and v prime in such a way. And then the inverse, before I run into the inverse problem, I want to say that in general, this nonlinear Boltzmann, the well-posedness for this nonlinear Boltzmann equation is open. We are only going to study the case that we have small data. So we are going to assume that this collision kernel K is in some admissible set, and we consider some small data in terms of this L infinity norm, and then we can prove that this inverse boundary value problem has a unique solution and it satisfies this kind of equality. So in connected theory, this kind of small data is corresponding to the situation that you set up everything in a near vacuum situation, in a near vacuum background. And now we are ready to define our measurement operator. So we are going to measure this boundary and initial data, then mapped to the outgoing incoming boundary incoming data to the boundary outgoing and final data. So the question here is, from this measurement operator, can we determine the collision kernel K? And I want to remark here that compared to this linear Boltzmann equation, we also measure some initial data and final data. This is needed because we are talking about time-dependent collision kernel K. This is the same situation as in this linear Boltzmann equation if you want to consider time-dependent coefficient. So if you only measure this incoming and outgoing data, there will be a region that there will be a clock region, and you cannot extract any information from that area. And some previous literatures on nonlinear Boltzmann equation, this was first studied by Ru Lai, and Woman Yang in 2021. And they studied the stationary nonlinear Boltzmann equation, and they gave uniqueness and reconstruction procedure. And for this dynamic nonlinear Boltzmann equation, this was only studied by Lili Yang in 2022, but they studied this uniqueness result near the equilibrium point. So which means their initial data is a Maxwellian, and they use Gaussian-Weierstrass transform, and they only consider the collision kernel K has this structure, has a product structure, and where this theta is given by this the angle between those two velocities. And compared to this linear Boltzmann equation, when we consider nonlinear Boltzmann equation, we cannot use their results directly. The reason is we have this post and pre-collision velocities, and this is the phenomenon that the linear Boltzmann equation does not have. And now let's assume some assumptions on our result. We are going to assume, like in Bellasfield and Begans paper when they discuss this time-dependent coefficient, we are going to assume that our K has a product structure. So our K can be split into two pieces. The first piece, I have my time, I have my position, and I have the absolute value of V. And this C is my unknown function that I would like to recover, and this psi is some known function. And in the future, because I let my phi depend on the absolute value of V, I'm going to denote R to be my absolute value of V. And I'm also going to assume that this phi function is strictly positive on certain sets. This is needed because I would like to finally split my unknown part from this known part. And here is our result. So we let AK1, AK2 be two measurement operators of the problem with Clarion kernel K1, K2. We assume some regularity for our function C and C. We also assume that the difference of those two unknown functions is compact supported inside my time and space domain. Then, if we assume the measurement operator applied on my small data is bounded by some constant that is less than 1, then we can get that our unknown function phi1 and phi2 is bounded logarithmically by this delta here. And if we assume better regularities for our function phi, we can also get a uniqueness result. So we can get this phi1 actually equals phi2 in this domain. And now, at the end, I would like to briefly introduce the idea used in the proof. So we consider the solution for my nonlinear Boltzmann equation, and I'm going to use the second order linearization. So I'm going to feed them with small data, small boundary data, and small initial data. And then we can write down an expression for my function in terms of epsilon and the first order linearization functions and second order linearization functions paired with quadratic terms, and we also have some remainder terms. And where this F1, this V1, V2 solves my first order linearization, so which is just a free transport equation with some boundary data. And note here this V1, V2, they are independent of the Clarion kernel K. And this WK1, K2, this is my second order linearization, and it is the unique solution to the free transport equation, but with some source term on the right-hand side with 0 boundary data and initial data. So in particular, if you have S11 here, so S11 looks in the following form. So in S11, you have your unknown Clarion kernel, and you also have some first order, the solution of the first order linearization term. Because we are doing everything, we are doing the stability result, so we would like to have everything in a quantitative way. So we are going to use the following second order finite difference operator of this function at epsilon equals 0. And this is given by this formula right here. So when I write this f epsilon 1 g1, epsilon 2 g2, which means my f solves my initial boundary value problem for this nonlinear Boltzmann equation with boundary data epsilon 1 G1 plus epsilon G2 with initial data epsilon 1 H1 plus epsilon 2 H2, and similarly for all those terms. And now if I take the finite difference for my F operator evaluated at 0, what I get is my second order linearization function W11 plus the finite difference, second order finite difference of my remainder term. Remember that in our previous page, we know that the source term of the second order linearization function, it contains information for our Clarion kernel. So what we're going to do is we're going to just apply the free transport equation on both sides. Then if I apply the free transport equation on both sides, this term will become my source term S11, and I have the desired information for my Clarion kernel K inside. Our next step is to bridge our known data, our boundary data, with our interior data. So if you look at this part is the interior, and this side is also interior. This side is something we want to know, but for this F, we know it's boundary data. So we simply multiply by a solution of the free transport equation and do integration by parts. So after we've done this, what we have is, this is the right-hand side in the previous page. This is the information we know, we want to know, and for the first term, for the left-hand side in the previous page, we can use the integration by parts to translate them into the boundary data we know, and we have some error terms for this epsilon here. And now let's come back to our problem. So we let AK1, A1, A2 to be the corresponding measurement operator for the Clarion kernel KL. And then if we take the difference, what happens is we know that the difference, the measurement operator acts on small data, then we take the difference, this term will be very small, and this is just some error term. So what we now have is we have the integral for my function S with of C. This is bounded by some term that is small. And now what we would like to know is, we still would like to extract information from the source term to get our desired function phi. So our first step is we take the function for this transport equation, and then so the function for this free transport equation, we have a lot of freedom to choose the solution. So one particular way is we just choose this C equals Cx minus Ty. If we do this, and then we do change a variable, this is a function phi here, and phi, this function is arbitrary. So what we are going to do is we are going to locate this function we are going to use this, we are going to locate our integral at a particular point. So we let our function approach some delta distribution, then we get the information about this integral S, and we have this phi tilde is the term we want to recover, and we also have the unknown, and we also have some data that comes from this first order linearization, the solution of the first order linearization. So our next goal is to move all those, bound all those, and then get a bound for our unknown part. So in order to do so, we are going to choose some special solutions to this first order linearization. So remember that the first order linearization is just a free transport equation, and we we can simply choose our function that is independent of time and x. And in such a way, we choose our v1 just to be an exponential function, and we choose our v2 to be a constant function. What is good about this is, first, it satisfies the free transport equation, and it also satisfies it does not change the sign when you evaluate it at this v prime point. And this equality only holds on a set of measure 0. So it's kind of bounded a little bit away from 0. And then we also know that this function phi is bounded from below on a certain set, and then use those two information, we can put all those integral away to the other side. Now what we have is this scaled library transform of my function is bounded. So from here, what we are going to do is we are going to use a Fourier slice theory. We multiply by some exponential function, then we integrate over space. Then we get the Laplacian transform for this Fourier transform. Using that, my phi theta is compact supported. We also have this part is compact supported. And therefore, we may bound the Fourier transform of this phi theta in such a region which is a space-like call. So note here, this is only true when my tau variable, it has a very special product structure. So tau is the Fourier transform corresponding Fourier parameter in t direction, and c is the corresponding Fourier coefficient in this space. And after we bounded the Fourier transform in a space-like cone, we are going to use the fact that this function, Fourier transform for this function, is analytic and it has almost polynomial growth. We use an argument by Vassola in 1999. We can extend the boundedness of this Fourier transform phi theta to a ball with radius alpha. So it's not a space-like cone anymore, but in a ball. And now, in order to compute the H-1 norm of my phi theta, we are going to split this into the low frequency part and the high frequency part. And for this piece, we are going to just use Planck-Chern theorem. And for the first piece, because we have the Fourier transform and this is in a ball of radius alpha, we can use the previous bound we get to bound this term. And then by choosing alpha, choosing alpha to minimizing this right-hand side, we get a logarithmic stability result for H-1 norm for my phi theta. And this completes the proof of the stability result. And to get the uniqueness result, to get the uniqueness result, all we need to do is we do an interpolation and we use the result for the stability result. And this is my talk. Thank you very much for your attention.
Thank you very much, Lili, for the very nice talk. Thank you very much. Are there any questions or comments, please? Please feel free to unmute yourself. Any questions or comments? Any questions or comments, please?
Hi, Lili. This is
Hi.
Yang. So
Yeah.
your slides, page 16, I guess we'll talk about
page 16.
decomposition. Yeah.
Yeah.
Yeah. So the decomposition will be F1, F2, F3, right? Could you explain? So how to derive this F3 here? This is like the second order singular part, or?
Okay, so F1 is okay, so in dimension n greater or equal than 3, so F1 is the most singular part, and F2 is the least, is the next second singular part, and F3 is like the least singular part. So this F3, this function is actually if you multiply by a factor, this F3 is some L infinity function.
Okay, so okay, so when you apply when you derive F1, F2, and then you have some equation for F3,
left term.
you can derive this is a L infinity function. Okay, got it.
Yes.
Thank you for the explanation.
Thank you for the question. Yeah.
Thank you very much. Are there any other questions or comments, please? Any questions or comments, please? Okay, if not, thank you very much, Lili, for the very nice talk. Thank you very much. Thank you very much, everyone, for coming. Thank you.
Thank you, Katya.